And we're back. Welcome back and happy Thursday. Today, we will move on to methods for controlling overfitting, namely regularization. But before we begin, some administrative bits. The reading. Chapter 4, Section 4.1 is on overfitting. Section 4.2 on regularization. And Section 4.3 is on validation. The focus of today is regularization. And so when we last met, we talked about stochastic noise and deterministic noise. And we said that the overfitting behavior of either was the same. But the good news is that as you increase your data set size, number of in-sample points, stochastic noise and deterministic noise overfitting goes down. But as stochastic noise and deterministic noise both increase for a given number of data points, your overfitting increases. And so we talked about how you deal with noise, and we talked about this idea of restricting your hypothesis, a so-called restrained fit. So this regularization is the focus primarily for today's module. So let's take a look at the intuition. Now, mathematical function approximation, when you have an ill-posed problem, there are multiple solutions from which you can choose. And the solution, or the best solutions, when you have many from which you can choose, is to choose the smoothest solution. And you can add constraints to that effect in order to encourage the selection of smooth solutions. Now, in Bayesian methods, they directly encode this idea of smoothness with the prior distribution encoding domain knowledge. And so effectively, when you have an optimization problem, one way you can impose this smoothness is to add a penalty term to the optimization problem and then solve the gradient of this new version of in-sample error, try and set it to 0 and solve for your hypothesis W, weight vector. So let's consider this idea of a restrained fit. On the left-hand pane, we sort of bring back our sinusoid, and we had a data set of size 2 that was sampled uniform at random from the sinusoid unknown target function. And then we fit a line, unconstrained, with parameter slope and y-intercept to these two data points sampled again and again and again from our target function, our sinusoid. Without any regularization, we get the following. We get these very wild lines as well as more typical lines. But if we were to constrain both the slope and the y-intercept for the line, limit how big they can be, we don't get as many wild lines as it's trying to fit. We don't allow it to choose wild solutions. And so you can verify using bias variance analysis about the impact of this restraint on the parameters, slope and y-intercept, for arbitrary lines. And so let's bring back this idea of the best hypothesis we can get, our G-bar. And in the unrestrained fit, our G-bar bias is 0.21, and that was from before. And the variance, as we had from before, the gray region, was catastrophic, 1.69. But with our constrained version of the fit, one of the things you'll notice is that the bias is a little bit increased. And the reason for that is that it doesn't have the horsepower, the ability to be wild enough to pursue with specificity those two data points sampled from our target function. So we get a slight increase in bias when we restrain the fit, but the good news is that the variance is far less, it's 0.33. And so regularization ended up decreasing the variance, and the trade-off was a modest increase in bias. And so when we restrain or handicap the fit, this resulted in a slight loss in the quality of the fit, but the overall benefit was this reduction in the variance. And so essentially we started out in this solution for the restrained line by limiting the y-intercept and the slope to some degree. it resulted in a solution that was certainly better than the unrestrained fit, and it was also better than the constant line. And so essentially what we need is something in between full quadratic, linear, and constant, and that's essentially what regularization achieves. It strikes this notion of in between. So you get the expressiveness of a more complex hypothesis set, but you don't overdo it with the expressivity, the degrees of freedom, the ability of that complex hypothesis set. You're limiting its ability to bend and twist and fold. And so let's take a look at our regularization formulation. And in this, we're going to form a complex hypothesis set, and this complex hypothesis set is going to consist of a polynomial of degree q. And we're going to achieve this through a transformation to feature space, and our phi function is going to consist of the Legendre polynomials. And so there are the first 5 order monomials from the Legendre polynomials. And when you put these together through weighted combination, you get a polynomial of degree q. Now, the special feature of these Legendre polynomials is that the individual monomials are orthogonal to one another. And so we can use the Legendre polynomials on the input x to form a point in feature space where each one of the features corresponds to one of these Legendre monomial terms to transform our input x. And so HQ is a q order or degree q polynomial, which is a weighted combination. So we have a weight vector to choose different hypotheses, but this transformation to z-space is achieved through the Legendre polynomials. And so this gives us a nice nonlinear mapping, and we're going to use this as our hypothesis set, and we're going to use this for learning. So let's imagine we're given a set of labeled instance pairs, our data set x1, y1 through xn, yn. So we have big N, many points in sample. And we're going to transform them through the Legendre polynomials to z-space. And we have a one-to-one mapping, z1 through z big N. And so if we were going to minimize in-sample error, let's imagine this is a regression problem. And so we have our W transpose Z, so it's in feature space, this regression model. And we're going to use the squared error loss function in formulating our in-sample error. So we get our expression 1 upon n. The sum for n goes from 1 to big N over each one of our in-sample points. We have the score W transpose Zn, and of course this is in feature space, minus y, our label assigned by the unknown target function. We take the square of that difference. So our point-wise error in this case is the squared error loss, but it's in z space. Okay, so if we take each one of our z's and we put them in a design matrix, or a design matrix big Z is a row matrix consisting of little z transpose 1 through little z transpose big N, we can, in vector matrix form, come up with a closed form solution for in-sample error more conveniently in vector matrix format. So of course, this is exactly like the regression that we solved before, and the solution we're going to call WLin for this unconstrained linear regression solution, which is just the pseudo-inverse of in Z space. So we get Z transpose Z inverse times Z transpose Y, which is our pseudo inverse in Z space. Okay, so this is our unconstrained solution. Now let's pose a constrained version of our hypothesis set, and let's imagine we had a degree 10 polynomial hypothesis set. We'll call that H10. So let's imagine we constrained our degree 10 polynomial hypothesis set. And so let me write out our polynomial, and we're going to say W naught x to the 0 power plus W1 x to the 1 power plus W2 x to the 2 power plus all the way up to and including W10 x to the 10th power. So there's our polynomial. Now, of course, if we set our W's to 0 everywhere we had a degree greater than 2, we're effectively shutting off each of those monomials for degree 3 up to that 10th exponent. Now, that's pretty dramatic, and what you're essentially doing is you're limiting the expressiveness of a degree 10 polynomial to a quadratic. Now, one of the things we can do is strike a balance, this idea of having some of the expressiveness of a degree 10, but you're kind of putting a constraint on it. And we can do that using a soft constraint. And the soft constraint is of the following form. We have Q goes from 0 to big Q, the degree of the polynomial, WQ squared, if that sum is at most a budget that we're going to call C. And essentially what that's doing is it allows us to use all of the monomial terms in our polynomial hypothesis set. But what this C is doing, C is a value, and it's saying I'm going to carve out of this budget, this C, all of these weights that I can spread now across all of the monomials making up this polynomial. So if C is very small, these weights are going to be very small, and my contributions of each one of these monomials from the 0th power through the 10th power is going to be relatively minor. Now, if C is a relatively large budget, a large value, that means that I'm going to have more budget to contribute or spread out to each one of these weights, and I'm going to get bigger weights over all of the monomials for a more expressive degree 10 polynomial. And so this idea of using a soft version of the constraint means I'm giving more to the weights, and I can use it for every way I can be expressive for that full set of the monomials for that degree 10 family of polynomials for my hypothesis set. And so if I do that, then I can then take my expression for in-sample error, the squared error loss in vector matrix form, just a minimization problem, 1 upon n, my design matrix ZW minus Y transpose ZW minus Y, the squared error loss in vector matrix form, subject to this constraint. W transpose W is at most my budget C. And so the solution to this problem I'm going to name differently. I'm going to call it W-reg for the regularized regression solution instead of W-lin, the linear regression solution. And so let's look geometrically at what this constrained optimization problem means. Now I have my in-sample error, that's my squared error loss. And in-sample error, for each value of in-sample error, I'm going to run minimization, and in-sample error, if I walk down the gradient, is going to get smaller, smaller, and smaller. Now if I look at the terms here I have in Z-space, I have each position or each feature in Z-space times a constant W, and I'm multiplying it by itself here. And so that looks like an elliptical shape, and each contour line represents a constant value of in-sample error, and it's elliptical. So when I walk down the gradient for En, looking for my W-linear regression solution, for each value of in-sample error that I encounter, I'm going to get a concentric circle here, and it's going to be elliptical because this squared error loss is an ellipse. Okay. And so if I minimize in-sample error, my W-lin solution, that's where in-sample error goes to 0. I get this point right over here. That's W-lin. Now, my constraint here, W transpose W, that's a circle. It's an ellipse that has the same coefficients for each one of the axes, and it's at most c. And this is this red circle. That's my constraint, W transpose W. The biggest budget I can have is the equality part, where W transpose W is precisely equal to C. Now, of course, if my budget is as small as possible, that's this black point here, where my constraint is equal to 0. That's the minimum. Now, I go all the way out to constraint equals C. That's the edge of this circle. And so when I look at my gradient of in-sample error, I walk down the gradient and I get a smaller concentric circle, until eventually I get to in-sample error equals 0, which is this W Lin point. Now, if I go in this direction, walking down the gradient, that means the gradient of in-sample error is this point that's orthogonal to this ellipse for these concentric constant lines for in-sample error. Now, of course, it's orthogonal because these circles are concentric, and so either I move inward towards W Lin or outwards away from W Lin if in-sample error increases. And so I can draw this blue edge that orthogonal to the ellipse for in-sample error equals constant, and that's going to be the gradient of En. Likewise, when I look at my constraint, if my constraint goes to 0, smaller, it goes towards the center here in this direction. And when my constraint is equal to C, the largest value, well, my constraint is going to be either moving inward, concentrically with this red circle, or outward. And so this biggest constraint in the direction of W Lin is going to be this normal going outward, this red edge. It's going to be an orthogonal to the surface of this red circle. Now, of course, when I minimize in-sample error, it wants to pull my solution closer and closer to W Lin, but it can't violate that constraint. And so here, my gradient of in-sample error is in this direction, the blue arrow, orthogonal to the contour for in-sample error. And my constraint is this red arrow, orthogonal to this red surface, the constraint circle. And so my solution for W Lin can't go any further than this constraint because I can't violate that constraint. It's less than equal to this C. So that means whatever solution I have is going to be somewhere along this red circle, but it's going to be as close as possible to this W Lin. Now, of course, we said that this red normal to this constraint is pointing outward, and this blue normal for the gradient of En is orthogonal to the contour line associated with En equals some constant. And so essentially what we get for the gradient of in-sample error when I'm minimizing it, it can't go any closer to W Lin than the surface of this red constraint circle. So that being the case, that solution is W reg. And that means the gradient of En evaluated at this W regularized solution on the surface of this constraint circle is going to be equal to the negative of the W reg, proportional to. And so this proportion represents the fact that here I have my constraint that won't allow my W Lin solution to get any closer. And I know my gradient, En, is in the opposite direction of my constraint respecting this budget C. So I write this gradient, En, evaluated at that W reg solution is proportional to the negative of that W reg, because En is opposite to that W reg constraint. And so here, out of convenience, I'm going to rewrite this proportion to make it convenient because I know I'm taking a gradient of something, and I know that it's going to include a square term because I see W transpose W. And so when I take a derivative, I want to undo something involving a square and a derivative. So I'm just going to write a 2 here and multiply by n because it's still proportional to. I'm going to add in this parameter lambda that's going to allow me to control how much of the influence I'm going to have for this constraint. So I have my gradient of in-sample error. I have my constraint portion. And now I'm going to do a little bit of algebra. So I'm going to add 2 times lambda upon n W reg to both sides of equality. And I get this expression, the gradient of En W reg plus 2 lambda upon n W reg is equal to 0. Now, if I look at this solution, this looks like it's the result of taking the derivative of something. And the derivative of that something is going to be obtained by, if I took the integral of this expression, well, that would mean this is the derivative of some original expression, which is En of W, because I'm going to get that W reg solution from minimizing En. So the derivative of that is the gradient of En. And then this value is the result of taking the derivative of W transpose W. Because if it's something squared, the derivative is 2 times lambda upon n W. And so this is my equivalent expression, and it relates my constraint C to this penalty term through my lambda. And so essentially what this means is that I can satisfy this constraint subject to this soft budget for the weights in an unconstrained fashion with this augmented in-sample error. And so this lambda is my regularization parameter. And if my C is really large, it means I have a more generous budget for my weights, and that's going to correspond to my lambda being small. If I have a generous budget for C, that means if this constraint circle is big enough, eventually it will envelop the W-lin solution. And if it envelops the W-lin solution, it means that when I select weight vectors W, this impact on the minimization for this penalty term is going to be very small. So lambda has to be small, corresponding to C being big. Consequently, if I have a budget that's really small, C is really small, that means my constraint is going to pull that optimal solution away from the W-lin. And that C being small corresponds to lambda being big, so that we're now paying not attention just to minimizing En, but also making sure if lambda is big, that these weights are going to be relatively small because we want this sum to be very small as a result of our solution. And so this relationship between this constraint, we can represent that constraint for our soft budget, limiting the complexity, as it were, of our hypothesis that by an unconstrained equivalent problem with this penalty term, and this regularization parameter controls how much we pay attention to that constraint. Okay, so let's look at our minimization problem with our augmented in-sample error, call it EOG, which is in-sample error plus our penalty term. Now, of course, from before, in-sample error using that Legendre polynomial bifunction, the feature space, this was our results from before, and we're going to add our penalty term for our unconstrained version of that soft constraint. And that's going to be the equivalent of our original unregularized regression problem subject to this constraint. So this one has conditions, but this first one, this augmented in-sample error, has no conditions, and we can solve this directly. Now, of course, with the condition version, this C is a complexity term. It's a soft complexity term, and this allows us to talk about something like the C dimension, because the larger this budget, the more complex your hypothesis set will be, because you're allowing these weights across all of the monomials for polynomial hypothesis set to be much more generous, and therefore that polynomial is going to make more or increase use of its degrees of freedom to bend and twist and fold more dramatically. And so let's take a look at our augmented error solution. Now, of course, for in-sample error, we have 1 over n, and we have a 1 over n for penalty term. So we can collect that common 1 upon n, and we have our in-sample error from before, and then we have our penalty term. Now, of course, if we take the gradient of this augmented in-sample error, EAUG, and set it to 0, well, if we set it to 0, we get the following result. Now, of course, we have a squared term, so we have a leading 2, and then we also have another leading 2 because this is squared, and then we have a lambda. So if we do that, there's a common 2 for these, and we can set that equal to 0, and then we divide both sides of equality by 2, we multiply both sides of equality by n, and because it's set equal to 0, we have the following result: Z transpose quantity ZW minus Y plus lambda W. Okay, so this is our expression for the gradient of EAUG set to 0. And we do a little bit of algebra. We get Z transpose ZW minus Z transpose Y plus lambda W is equal to 0. So we add Z transpose Y to both sides of equality, and we get Z transpose ZW plus lambda W is equal to Z transpose Y. So now we factor out the common W, we get Z transpose Z plus lambda I times W is equal to Z transpose Y. So we compute the inverse and we multiply both sides of equality. We right multiply by the inverse of Z transpose Z lambda I, and we get our solution we're calling W reg, for regularized regression solution, is equal to Z transpose Z plus lambda I inverse Z transpose Y. And that we're going to call W reg. So this is our solution to regression, our regularized regression solution that we can solve in one step using an augmented version of the pseudo-inverse. And then we contrast that with our unrestrained regression solution, W-lin, and the only difference is this regularization penalty term. And so that makes sense, right? Because if we increase our lambda, we're decreasing W reg, because this is in the denominator, it's an inverse. And so what this stands to do, as we increase the amount of regularization, our lambda, we're making the weight smaller and smaller and smaller. And W reg goes to 0 if lambda is big enough. Okay, so let's take a look at what regularization means. We go back to an earlier problem where we had a sample of 5 data points from a noisy quadratic target function, the blue curve, and then we had a degree 4 polynomial fit to this. Now, of course, we have our unrestrained fit corresponds to our regularization parameter, lambda equals 0. That means we're not paying attention at all to the constraint and just minimizing in-sample error. Now, with a little bit of regularization, little goes a long way, 0.0001, we get this smoother much better, more constrained fit from our degree 4 polynomial. And our out-of-sample error, you can see, is much, much better. But too much of a good thing is not always correct. If we have even more regularization, lambda is much bigger, 0.01, it starts to flatten out because now we're beginning to over-constrain our degree 4 polynomial to be too flat. Our weights are going to be too small. And then it flattens out and we start underfitting for lambda equals 1. In the case of lambda equals 1, we pull our solution so far away from the WLin that it's paying more attention to making the weight small versus minimizing in-sample error. All right, so let's take a look at this idea further of weight decay. And this is the most popular form of regularization, and we're going to explore why it's called weight decay. So when we do the gradient descent, we say our weight vector at time t plus 1 is the old weight vector minus step size eta times the gradient. Now, of course, if we compute the gradient, we have the gradient of En, and then we have 2, because this is a square term, times that step size lambda upon n times w. So here we take our gradient En w times step t minus 2 lambda upon n w at time step t, and we multiply this times our step size eta, and we subtract this from w. Now, if we collect the terms, all those terms that have a wt, well, we have this, that's 1, minus 2 eta lambda upon n w times step t. So we collect together those terms, we get w times step t times 1 minus 2 eta lambda upon n minus our step size eta gradient of En wt. So if we look at this term, what this ends up doing is this is less than 1. And because it's less than 1, that means our weight vector is being shrunken, made smaller, and then we move in the direction of the gradient. Now, if we keep doing that again and again and again, eventually our weight vector gets smaller and smaller and smaller, and it's the name weight decay. Now, this also applies in neural networks, where in a neural network we have all of the weights for all of the layers, from all of the inputs to all of the output nodes. And we have that square of each weight component. And that's our penalty term that corresponds to weight decay in a neural network. All right. And so another method we can do specific to the neural network is that we can emphasize whether the high order terms or the low order terms get decayed more or less, or counted more or less, by tinkering with the penalties, making them different based on the layers or the order of the fit. And so in one case, we can take our penalty, our squaring of the weight vectors, and we modulate them by this gamma. And what gamma for the low order fit is going to be 2 to the q, the order of the polynomial. And what that means is that the penalty is going to be much bigger for the higher order monomials in that polynomial. And that's going to now encourage the low order terms to be used for the fit, because the optimization wants to avoid the larger penalty. On the flip side, we can encourage a higher order fit. If we have a penalty that's 2 to the minus q, these are going to be diminishingly small, and those weights are going to go to 0. So the emphasis is going to be on the higher order terms. As q gets bigger and bigger and bigger, this is smaller, smaller, smaller. So the impact of increasing the higher order monomial terms in your polynomial is going to be less painful to the optimization. So it's going to encourage higher order terms when it's selecting a hypothesis. Put more weight there because it doesn't get counted as much for this penalty. And so in a neural network, different layers can get different gammas. And this is a very popular approach called Tishanov regularization. So we can place different emphasis on the different layers in a network across the weights. Okay. And so when we have stochastic noise, typically high frequency, and deterministic noise is also very wiggly, as it were. It's non-smooth. And we tend to want to constrain our learning so that we prefer smoother hypotheses. And so smaller weights in general are associated with smoother hypotheses. And if you have regularization parameter, lambda, increasing, you start out, your weights get smaller and smaller and smaller, and then you start to underfit, and your out-of-sample error blows up. You could also have your weights get big in the beginning, have weight growth. Your out-of-sample error is going to blow up. And so you start out overfitting, and then as your parameter lambda increases, you get better and better and better until you overdo it and you start underfitting. And the impact of underfitting is that your expected out-of-sample error also gets large again. So you want to strike the right balance, and a little bit of regularization goes a long way. If you overdo it, it's like medication. Too much is not always a good thing. And so when you have hypotheses, you can impose a regularizer on that hypothesis to effectively repair having an overly complex hypothesis. And so we said this augmented error is the in-sample error plus this penalty term. And this penalty term is a regularizer. And what this regularizer serves as is a limit on the complexity of your hypothesis set. So we can treat this regularization term, this penalty in our optimization for EOG, our augmented in-sample error, we can treat that penalty term as if it were the complexity of the hypothesis set, because that's essentially what it is doing when we add that constraint, that C value, talked about a few slides ago. And so this is going to seem very familiar. It rings a bell because it almost looks like our expression for out-of-sample error. When we talked about the VC analysis, VC dimension, we said E out is at most E in plus that complexity of the hypothesis set. E augmented is better than E in as a proxy for E out, which is essentially what our regularization is doing. It's expressing a limit on our complexity and allowing us to estimate out-of-sample error as a function of E in. All right. So let's look at how you choose a regularizer. Now, ideally, a constraint represents solutions in the direction of the target hypothesis, and you hope that the smooth path to get there is simpler and not wandering. And so if you have a bad penalty function, you can certainly reduce the impact of that bad penalty function, that regularization term, by having a very small lambda. And so the damage can be mitigated by just tuning down the impact of that grossly off penalty function, this regularizer. And so here in a neural network, we talked about the hyperbolic tangent as being a medium between a hard threshold and a linear threshold, depending on the score. Now, of course, with weight elimination, you can, in a neural network, set your complexity so that if your weight drops below a certain amount, you actually set it to 0, and that has the added benefit of reducing your complexity because you're turning off some of your weights or some of your parameters, just setting them to 0. And so this idea of smoothness can also include complexity reducing weight elimination. Because you eliminate a weight, set it to 0, shunt it off to 0, you're also reducing the dimensionality, i.e. the number of parameters, and therefore reducing the complexity in the VC dimension sense. Now, of course, you could also do this through early stopping. You can say, well, take your quantity to be minimized, put it in the objective function, evaluate the impact, and just stop when you see overfitting start to happen. Now, if you're going to choose a lambda, in this experiment, we have stochastic noise, and stochastic noise was defined in terms of a fixed complexity target function along with our regularization parameter. And as you increase the regularization parameter, watch what happens as you increase stochastic noise. Now, stochastic noise in the beginning, if there's no stochastic noise, sigma squared is 0. If you increase the regularization parameter, well, you're going to start to underfit, and expected out-of-sample error starts to increase. But if you start with some stochastic noise and you increase your regularization parameter a little bit, it overcomes the stochastic noise, and you notice the expected out-of-sample error goes to 0, but then you overdo it, it starts to increase a little bit. You're starting to underfit. Likewise, if we have even more stochastic noise, we need more regularization, so the parameter is bigger. We see the expected out-of-sample error drops, and then there's a point beyond which we overdo it, and it starts to increase marginally. But what we notice here is that we don't have any regularization parameter, a little bit and more, as a direct counterbalance to stochastic noise. And we see the same behavior with deterministic noise. So here we have our regularization parameter, and we have a deterministic noise for a target function that is degree 15, 30, and 100. And we notice with no regularization, well, we increase the parameter, we're underfitting, expected out-of-sample error increases. With a much more complex target function, a little bit more regularization is needed, and we see expected out-of-sample error goes down. And then we overdo it, and it starts to increase or start to underfit. And the same thing with degree 100 polynomial target function. We need even more regularization. Expected out-of-sample error drops, and then eventually we overdo it, and it starts to increase again. So we see the same behavior vis-a-vis regularization parameter lambda for stochastic noise, the same behavior with deterministic noise. And so it just says, as you turn up the noise, you need more regularization to counteract the overfitting. But if you overdo it for both stochastic and deterministic noise, you're going to start to underfit. Little regularization goes a long way. Okay, so with that, that's all I had for today. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.